Okay, so our purpose here is to modify Bellman-Ford such that if there is a negative cycle reachable from the source, Bellman-Ford would stop and says there is a negative cycle reachable from the source. This graph I cannot handle correctly, bye-bye. So how do we do that? Well, we prove a rather simple claim that says the following. If there is a negative cycle reachable from the source, then the distances do not stabilize in the nth iteration. What do I mean by that? You look on the distances computed in the nth iteration, you look on the distances computed in the n-1 iteration, and there is one vertex where this distance shrunk. Okay, so let's prove that. So the basic idea of the proof is to say is by contradiction. Let's assume that this doesn't hold. What does it mean? It means that for all the vertices in the graph, this is in fact larger equal, the distances, the end distance is larger equal than the distance n-1. But to remind you, dvn, when we compute it, is the minimum of dvn minus 1 and some new value. Right? dvn can only be smaller equal, which means that in fact what we are really assuming is that the values are equal. Namely, for all the vertices in the graph, the distances in the end iteration and the n-1 iterations are the same. But there is a negative cycle reachable from the source. So let's look on this negative cycle. And for this negative cycle, we can write a system of inequalities, right? So consider the cycle to be V0 going to V1 and so on. You're going around the cycle. Where V0 is, let's say, the first vertex reachable from S, right? The nearest vertex to S. It doesn't really matter how we choose it. But now let's write down the quantity. The important thing, of course, is that dvn and dvn minus 1 is defined for all the vertices of the cycle because they're all reachable from S, they're all reachable by paths, so these values are finite. So we can write things with those values. And now the inequality says, well, the distance of getting from the source to V1 with a walk of n edges is smaller than the distance to go to V0, the previous vertex on the cycle, with n-1 edges, plus the price of the last edge, V0 to V1. This is just the triangle inequality, right? Saying that you go to V0, you continue to V1, and the distance from S to V1 is smaller than the distance from S to V0 plus the price of the edge, where here we have to pay n-1 because we are looking on the previous, we are looking on the shortest walk using only n-1 edges, right? So this inequality must hold, right? And it must hold for all the vertices in the cycle. So you write it down for all the vertices in the cycle and all the edges in the cycle. So we get this system of inequalities, right? Now, the important thing here is that by our assumption, the distances in the nth iteration and n-1 iteration are the same, which means that really the quantities written on the right side and the left side are the same quantities. They're shifted one row down, essentially. They are circularly shifted, but we get these inequalities where this column is just the sum of for every row, it's one edge of the cycle, and we get all the edges on the cycle. So if we add up all those inequalities, we get this summation. Okay, so we have this summation. Now let's look on this summation carefully. This and this are the same thingy, right? So we can cancel them out. And as such, we have the following, right? We cancel this with this, because they're the same, so we get this inequality, 0. This is the sum over the edges of the cycle, right? I go from 1 to k, and then we also have to take the last edge from vk to v0, right? So this is the total length of the cycle. 0, we have 0 larger than that from this inequality, right, above. That's how we got to this inequality. But what's written on the right side, what's written here, this is just the total length of the cycle. This is the total length of the cycle. And if we ignore this, right, we just keep this, we remove this portion, what we got is that the length of the cycle is larger or equal than 0. Namely, this is not a negative cycle, which is a contradiction. So we are done. We proved that indeed the distances cannot converge if there is a negative cycle reachable from the source. Okay. Previously, in earlier lemma, we proved some complement claim. The complement claim was that if there is no negative cycle, then the distances converge, right? They are the same in the n-1 iteration and the n+1 iteration. So if we put those two claims, this previously proved claim and the claim we just proved together, we get this new claim that says that G has a negative cycle if and only if the distances do not converge in the nth iteration. Right, so then that's all we need to do then. We just need to run Bellman-Ford till the nth iteration and see whether the distances converge or not. If they did not converge, we complain bitterly and declare that there is a negative cycle and we are done. And we got this form of Bellman-Ford, which is kind of the official version. So let's see what we are doing. We are doing the standard Bellman-Ford. Notice that we are back to the standard version where we do n-1 iterations in the top level, right? But then we do one final iteration. We do one final iteration and check whether one of the distances change. If one of the distances change, if we have one edge that is not relaxed, that we can improve the distances along this edge, we declare that there is a negative cycle and we are done, reachable from the source. And otherwise, we just copy the computed values to the array of the output and says, here are the distances from the source to the target, and that's it. Now, notice that we had paid dearly. So this algorithm works. It computes shortest path in the graph with negative weight, as long as there is no negative cycles. But we paid dearly for it, right? Because the extra works essentially in O of m time, right? It's n log n plus m, but let's ignore it for a second. The extra work in O of m time, and suddenly we got an algorithm that worked with negative edge, but the price of running this algorithm increased by a factor of n. So Bellman-Ford is quite expensive compared to the extra. But it's better to have something slow than not having anything at all.